Good afternoon, good morning, good evening, good night, depending on when you're watching this video. We are going to work through the first exercise on constructing a confidence interval, which is on slide 15 of lecture set 7. All right, so in this exercise, we have the following. We have an SRS. Well, it tells us that we have an SRS later, but we have an SRS of 10 scores from a competency test for all first-year university students. So in some previous examples from this lecture set, we defined the population, we defined the variable, which is the competency score. And we constructed what is called a point estimate for the population mean, which is simply the sample mean. So in previous illustrations, we computed the sample mean. So this is given earlier in the lecture set on 2 different occasions, including in the example on slide 14, that's right before this example. Now, in this exercise, we want to compute a 90% confidence interval. So it says compute a 90% CI for mu. That means 90% confidence interval. We are told sigma is equal to 20. We are told that we can assume the competency score is normally distributed and that the sample is a simple random sample. So when we're constructing a confidence interval or performing any sort of inferential method, the first thing that we do is check our assumptions. So for the confidence interval, we have the following set of assumptions. Okay. So the first assumption is that a simple random sample was collected. So usually I just use a shorthand notation for this. So I'll just write SRS, and we can check this off because we are told the sample is an SRS. And in most cases, we would have to know, based off the problem description, where the sample came from. There would have to be some indication that the observations were randomly selected, such that we can verify this assumption. The second assumption is that essentially what we want here is that the sample mean, we want the sample mean to be normally distributed. So there's 2 ways that we can get at this. We can either have a normally distributed population, or we can have a sample size that's large enough that the central limit theorem takes over. So I'll usually write the second one, the second assumption is, X bar is normal. And again, we can check this off because we are told in the question description that competency score is normally distributed. So the variable or the population is normal. That means that the sample mean will also be normal. Okay? And then the third assumption, which isn't really an assumption, but it's something that we require in order to build the interval in the way that we're going to build it, is that sigma is known. And we can see from the problem description that sigma is equal to 20, which means that it's known. So we're given sigma. And all this means is that we are going to build the interval using a z-score. All right, so now we will start to construct the interval. So we can write 90% CI. All right, the first thing that we have to do on step 1 is we have to find the z-score. So our confidence level is 90%. Okay, so I'll write conf level is 90%. Okay, so that means that alpha is 1 minus 0.9, which is equal to 0.1. Okay, so alpha is simply 1 minus the confidence level as a decimal point. So our confidence level is 90%. So that's 0.9. So 1 minus 0.9 is 0.1. So that's the significance level alpha. Now what we need is a z-score. So we need z subscript alpha over 2, which is z subscript 0.1 over 2, which is z subscript 0.05. All right, now this is from our previous discussion on the same nomenclature, this is the z-score that has 0.05 of the area to the right. All right, so we could sketch this out. Over here. So if I was to just draw a little standard normal curve, so something that looks like this. Okay. So we have Z 0.05. Okay, so this red shaded part here is a size 0.05. So we want the z-score that puts 0.05 in the upper tail. So if we have 0.05 in the upper tail, that means we have 0.95 to the left of that z-score. Okay, so we go back to our standard normal table now. Hopefully all of this looks familiar. These are the same techniques that we were developing in lecture sets 5 and 6. Right, we're looking for 0.95 in the table. 0.95 is one of those special z-scores that actually sits directly in the middle of two tabled values. So 0.95, the z-score that puts 0.95 to the left and therefore 0.05 to the right is the average of 1.64 and 1.65. Okay, so this is 1.645. Right. And we've seen a lot of examples of computing this particular z-score before. Now that we are into the confidence interval section of the course, it is recommended that you start to memorize some of these common z-scores. So for example, the z-score for the 90% interval is 1.645. The z-score for the 95% interval is 1.96. And the z-score for the 99% interval is 2.575. And once you have these values memorized, you can just use them whenever you're asked to compute these common confidence intervals. All right, so now that we have the z-score, we have to compute our interval. So the formula for the interval is x bar plus or minus z alpha over 2 multiplied by sigma divided by the square root of n. All right, now we're given sigma, that's 20. Little n is the sample size. There are 10 observations in this table, so little n is 10. And x bar is the sample mean for those 10 values. We've computed x bar in previous illustrations. Okay, so we've shown that x bar is 108.3. Okay, and that's from there's a few different illustrations of this value and the computation of this value on previous slides. Okay, so we have 108.3 plus or minus 1.645 multiplied by 20 divided by the square root of 10. All right. So that gives us 108.3 plus or minus, or plus and minus in this case, 10.403 or 10.404. Okay. All right, so this means that we have to go 108.3 minus 10.404 to 108.3 plus 10.404. So that means that our confidence interval has bounds 97.896 to 118.704. All right, and then we would finish off by interpreting. So for all confidence intervals, we have a standard interpretation. We would say we are the percentage confident that the population mean is between the lower bound and the upper bound. So in this case, we can say something like, we are 90% confident that the population mean competency score for all first year students, all first year university students is between 97.896 and 118.704. So you can see from step 2 and from the interpretation in step 3, what the confidence interval actually is a range. So it's two numbers that tell you with some percentage of confidence where we believe the population mean might lie. So we are saying in this case that we're 90% confident that the mean competency score for all first year students is between 97.896 and 118.704. All right, as always, if you have any other questions, please let me know.